So last meeting, we have discussed the following: single row function, features of single row function, types of function, categories of functions, examples, and illustrations. So for today, we will be discussing the following: continuation of the single row function, aggregate data using group function, group by, having clause, all and distinct keyword, classification of join like natural join, non-equality join, self-join, outer join, and Cartesian join. So using the group functions. So SQL has numerous predefined aggregate functions that can be used to write queries to produce exactly this kind of information. The group by clause specifies how to group rows from a data table when aggregating information, while the having clause filters out rows that do not belong in specified groups. So aggregate functions perform a variety of actions such as counting all the rows in a table, averaging a column's data, and summing numeric data. Aggregates can also search a table to find the highest or maximum for max or lowest minimum values in a column. As with other types of queries, you can restrict or filter out the rows these functions act on with the where clause. For example, if a manager needs to know how many employees work in an organization, the aggregate function named count, open and close parentheses with an asterisk, can be used to produce this information. So the count function shown in the below select statement counts all rows in a table. So we have the SQL statement here. So select count, open and close parentheses, asterisk from employees. So the employees here is the name of your table. So the projected output will be, for example, 24. So the result table for the count function is a single column from a single row known as a scalar result or value. Notice that the result table has a column heading that corresponds to the name of the aggregate function specified in the select clause. Commonly used aggregate functions, we have sum, all distinct expression, AVG for average, all distinct expression, count, all distinct expression, count with an open and close parenthesis and an asterisk, max for maximum, then expression, mean for minimum, then expression. So the all and distinct keywords. So the all and distinct keywords are optional and perform as they do with the select clauses that you have learned to write. So the all keyword is the default where the option is allowed. The expression listed in the syntax can be a constant, a function, or any combination of column names, constants, and functions connected by arithmetic operators. However, aggregate functions are most often used with a column name, except count function. All the aggregate functions do not consider null values. So there are two rules that you must understand and follow when using aggregates. So aggregate functions can be used in both the select and having clauses, and aggregate functions cannot be used in a where clause. Its violation will produce the Oracle ORA 00934 group function is not allowed here error message. So illustrations. So the below select query counts the number of employees in an organization. So same illustrations that we have presented a while ago. So select count, open and close parentheses with an asterisk, count from employees. So example, the generated output is 24. So the below select query returns the average of the salaries of employees in the organization. So we have select AVG for average, salary, average underscore sal from employees. So the sample output would be 15,694. So the below select query returns the sum of the salaries of employees in the organization. So we have select and then sum, salary, total underscore sal from employees. So example, output is 87,472. The below select query returns the oldest and latest hire dates of employees in the organization. So we will be using min and max. So select min for the minimum, hire underscore date, oldest, max, hire underscore date, latest from employees. So we will be generating the oldest and the latest hire dates. So example, we have 16 January 83 and 01 July 2012. Aggregate functions are normally used in conjunction with a group by clause. The group by clause enables you to use aggregate functions to answer more complex managerial questions such as what is the average salary of employees in each department? How many employees work in each department? How many employees are working on a particular project? Group by function establishes data groups based on columns and aggregates the information within a group only. The grouping criterion is defined by the columns specified in group by clause. Following this hierarchy, data is first organized in the groups and then where clause restricts the rows in each group. Guidelines in using a group by clause. Number one, all the dependent columns or columns used in group by function must form the basis of grouping. Hence, must be included in group by clause also. So, sample, select department underscore ID sum salary from employees, department underscore ID. So, error at line 2, ORA-00937, not a single group function. Number 2, group by clause does not support the use of column alias, but the actual names. Number 3, group by clause can only be used with aggregate functions like sum, AVG or average, count, max for maximum, or min for minimum. If it is used with single row functions, Oracle throws an exception as ORA-00979, not a group by expression. Number 4, aggregate functions cannot be used in a group by clause. Oracle will return the ORA-00934 group function not allowed, here error message. So example, below query lists the count of employees working in each department. So we have the statement select department underscore ID count asterisk from employees grouped by department ID. So similarly, below query to find sum of salaries for respective job IDs in each department. Note the group established based on department and job ID. So they appear in group by clause. So select department underscore ID, job underscore ID, sum, sal. From employees, group by department underscore ID and job ID. So the below query also produces the same result. Please note that grouping is based on the department ID and job ID columns, but not used for display purpose. So we have select sum salary from employees, group by department underscore ID, job underscore ID. So use of distinct all keywords with aggregate functions. So by specifying distinct keyword with the input parameter, group by function considers only the unique value of the column for aggregation. By specifying all keyword with the input parameter, group by function considers all the values of the column for aggregation, including nulls and duplicates. All is the default specification. The having clause. This is used to aggregate for aggregate functions in the same way that a where clause is used for column names and expressions. Essentially, the having and where clauses do the same thing. That is, filter rows from inclusion in a result table based on a condition. While it may appear that a having clause filters out groups, it does not. Rather, a having clause filters rows. So when all rows for a group are eliminated, so is the group. To summarize, the important differences between the where and having clauses are: a where clause is used to filter rows before the grouping action. Example, before the calculation of the aggregate functions. So a having clause filter rows after the grouping action, after the calculation of the aggregate functions. For example, so select job underscore ID, sum salary from employees, group by job underscore ID, having sum salary greater than 10,000. So we have here a conditional operator. So the having clause is a conditional option that is directly related to the group by clause option. Having, because having clause eliminates rows from a result table based on the result of a group by clause. So we have select department underscore ID, AVG average salary from employees having average salary greater than 33,000. So error at line 1, so aura dash 00937, not a single group function. So displaying data from multiple tables. So the related tables of a large database are linked through the use of foreign and primary keys, or what are often referred to as common columns. The ability to join tables will enable you to add more meaning to the result table that is produced. For n number tables to be joined in a query, minimum n minus 1 join conditions are necessary. Based on the join conditions, Oracle combines the matching pair of rows and displays the one which satisfies the join condition. Joins are classified as below. So we have the natural join, also known as an equijoin or a simple join. Creates a join by using a commonly named and defined column. So non-equality join joins tables when there are no equivalent rows in the tables to be joined. For example, to match values in one column of a table with a range of values in another table. So self-join joins a table to itself. Outer join includes records of a table in output when there's no matching record in the other table. Cartesian join, also known as a Cartesian product or cross join, replicates each row from the first table with every row from the second table, creates a join between tables by displaying every possible record combination. So let us first define and discuss the natural join. So the natural keyword can simplify the syntax of an equijoin. A natural join is possible whenever two or more tables have columns with the same name and the columns are join compatible. Example, the columns have a shared domain of values. The join operation joins rows from the tables that have equal column values for the same named columns. Consider the one-to-many relationship between the departments and employees table. So each table has a column named department underscore ID. So this column is the primary key of the department's table and a foreign key of the employees table. So example, select E dot first underscore name, D dot department underscore name, D name from employees, E natural join departments D. So we'll be having an output as shown in this slide. So it consists of two columns. The first column is for the first name and the second column is for the department name. So we have four rows as generated output. So we have Miller Department 1, John Department 1, Martin Department 2, and Edwin Department 2. So we just join the two department using this statement. So the below select query joins the two tables by explicitly specifying the join condition with the on keyword. So select E dot first underscore name, D dot department underscore name, D name, from employees, E join departments, D on, open and close parenthesis, E dot department underscore ID is equal to D dot department underscore ID. So there are some limitations regarding the natural join. You cannot specify a lob column with a natural join. Also, columns involved in the join cannot be qualified by a name, table name, or alias. So using clause. So using natural joins, Oracle implicitly identify columns to form the basis of join. So many situations require explicit declaration of join conditions. So in such cases, we are using clause to specify the joining criteria. Since using clause joins the tables based on equality of columns, it is known as equijoin. They are also known as inner joins or simple joins. So we have the following syntax. Select column list from table 1, join table 2 using column name. So consider the below select query employees table and departments table are joined using the common column department underscore ID. So we have the query select E dot first underscore name, D dot department underscore name, D name, from employees, E join departments D using open and close parentheses department underscore ID. Next, let's proceed with the self-join. Operation produces a result table when the relationship of interest exists among rows that are stored within a single table. In other words, when a table is joined to itself, the join is known as self-join. Consider employees table which contains employee and their reporting managers. To find manager's name for an employee would require a join on the EMP table itself. This is a typical candidate for self-join. Example, select E1 dot first name manager, E2 dot first name employee from employees E1 join employees E2 on open and close parentheses E1 dot employee underscore ID is equal to E2 dot manager underscore ID. Order by E2 dot manager underscore ID this. So this one is corresponds to a descending order. So next we have the non-equality join. So this is used when the related columns can't be joined with an equal sign, meaning there are no equivalent rows in the tables to be joined. A non-equality join enables you to store a range's minimum value in one column of a record and the maximum value in another column. So instead of finding a column-to-column match, you can use a non-equality join to determine whether the item being shipped falls between minimum and maximum ranges in the columns. If the join does find a matching range from the item, the corresponding shipping fee can be returned in the results. As with the traditional method of equality joins, a non-equality join can be performed in a where clause. In addition, the join keyword can be used with the on clause to specify relevant columns for the join. So example, select E dot first underscore name, J dot job underscore high sal, J dot job underscore low sal, E dot salary from employees, E join job underscore sal, on open close parentheses, E dot salary between J dot job underscore low sal and J dot job underscore low sal. So we can make use all comparison parameters discussed earlier like equality and inequality operators between, is null, is not null, and relational. Next, we have the outer joins. So an outer join is used to identify situations where rows in one table do not match rows in a second table, though the two tables are related. So there are three types of outer joins: the left, right, and full outer join. They all begin with an inner join and then they add back some of the rows that have been dropped. So a left outer join adds back all the rows that are dropped from the first or left table in the join condition, and output columns from the second or right table are set to null. A right outer join adds back all the rows that are dropped from the second or right table in the join condition, and output columns from the first or left table are set to null. So the full outer join adds back all the rows that are dropped from both tables. So the right outer join adds back all the rows that are dropped from the second or right table in the join condition, and output columns from the first or left table are set to null. Note, the below query lists the employees and their corresponding departments. Also, no employee has been assigned to department 30. So let's see. So we have here the statement and the sample output. So select E dot first underscore name, E dot salary, D dot department underscore ID from employees, E departments D, where E dot department underscore ID plus is equal to D dot department underscore ID. So we have the sample output consisting of three columns. So we have the first name, and then the salary and department ID. So as mentioned here in this slide, no employee has been assigned to a department 30. So we have John 6,010, Edwin 2,020, Miller 2,510, Martin 4,020, and then there are null values here for department ID 30. So left outer join adds back all the rows that are dropped from the first or left table in the join condition, and output columns from the second or right table are set to null. So the query demonstrated in the previous slide can be used to demonstrate left outer join by exchanging the position of the plus sign. So example, select that first underscore name, E dot salary, D dot department underscore ID from employees E departments D, where D dot department underscore ID is equal to E dot department underscore ID, then we have here the plus sign. So as seen in the slide, our output consists again of three columns. So we have the first name, the salary, and department ID. So we have John 6,010, Edwin 2,020, Miller 2,510, Martin 4,020, and a null value for department ID 30. So there are no specified first name and salary. So full outer join adds back all the rows that are dropped from both the tables. Below query shows list the employees and their departments. Note that employee man has not been assigned any department till now, so it is considered as null. And department 30 is not assigned to any employee. So let's see the statement. So select NVL, open and close parentheses, E dot first underscore name NVL, to underscore character, D dot department underscore ID, department underscore ID from employee full outer join department D on E dot department underscore ID is equal to D dot department underscore ID. So by the way, we have discussed last time the concept of NVL. So NVL stands for non-value logic, which allows you to replace a null value with another value. It's helpful when you want to store the fact that there is no data for a particular column, but you want to display something else. So aside from NVL, we also discussed the concept of NVL2, null if, case, decode, and coalesce. So the output for this particular statement is, so we have two columns here, first name and department ID. So as mentioned in this slide, employee man has not been assigned any department, as well as department 30 is not assigned to any employee. So we have man, it is considered as null value. John 10, Edwin 20, Miller 10, Martin 20, and then first name null again for the department ID 30. So there are 6 rows selected in this output. So Cartesian product or cross join. So for two entities, A and B, A asterisk B is known as Cartesian product. A Cartesian product consists of all possible combinations of the rows from each of the tables. So therefore, when a table with 10 rows is joined with a table with 20 rows, the Cartesian product is 200 rows. Why? Because 10 times 20 is equal to 200. For example, joining the employee table with 8 rows and the department table with 3 rows will produce a Cartesian product table of 24 rows. That is 8 times 3 is equal to 24. Cross-join refers to the Cartesian product of two tables. It produces cross product of two tables. So the above query can be written using cross-join clause. A Cartesian product result table is normally not very useful. In fact, such a table result can be terribly misleading. If you execute the below query for the employees and departments table, the result table implies that every employee has a relationship with every department. And we know that this is simply not the case. So we have select E dot first underscore name, D dot D name from employees E and departments E. So cross join can be written as select E dot first underscore name, D dot D name from employees E cross join departments D. So we have here some other illustrations and examples of the applications of order by. So the SQL order by clause is used to sort the data in ascending or descending order based on one or more columns. So some databases sort the query results in an ascending order by default. So we have the syntax here for the order by. Select column list from table name, where condition, order by column 1, column 2, up to the end column. So we have ascending and descending here. And the condition here for the where, you can use some of the relational operators such as greater than equal, less than equal, or not equal. So the following code block has an example which would sort the result in an ascending order by the name and the salary. So we have here the SQL statement select asterisk from customers, order by name and salary. So the select asterisk here meaning that we are going to display all the data or all the fields from the customers table. So this is the initial table, which consists of 5 columns. So we have ID, name, age, address, and salary. So this table consists of 7 records. So if we are going to apply this SQL statement, select asterisk from customers, order by name and salary, so our generated output would be on the right side of your screen. So we will arrange the name of the employees by ascending order. So instead of Ramesh, we will be having ID4, Chaitali, followed by ID number 5, Hardik, followed by ID number 3, Kaushik, ID number 2, Kilan, ID number 6, Komal, ID number 7, Mafi, and ID number 1 as Ramesh. Okay? So, next, the following code block has an example which would sort the result in the descending order by name. So we have the statement select asterisk from customers, order by name descending. So again, we have our original table, again consists of 5 columns, namely ID, name, age, address, and salary. And it consists of 7 records. So now we are going to see the output using this SQL statement, select asterisk from customers, order by name descending. So we have 1 Ramesh, 7 Mafi, 6 Komal, 2 Kilan, 3 Kaushik, 5 Hardik, and 4 Chaitali. So we have arranged the name of the customer in descending order. So the SQL joins clause is used to combine records from 2 or more tables in a database. So a join is a means for combining fields from 2 tables by using values common to each other. So as you can see in this slide, we have 2 tables. So the first table is known as the customers table, which consists of 5 columns, namely ID, name, age, address, and salary. And it consists of 7 records. So for table number 2, which is named as orders table, it consists of 4 columns. We have the OID, the date, customer ID, and amount. And it consists of 4 records. So for applying the SQL join, so we are going to combine the fields from these 2 tables by using values common to each other. And what are the values that are common to each other? So we have ID from table 1 and customer ID from table number 2. So let us join these 2 tables in each select statement. So we have select ID, name, age, amount from customers orders, where customers.id is equal to orders.customer underscore ID. So from the original table, which is our customers table, again, it consists of 7 records with 5 columns. And table number 2, orders table, consists of 4 columns with 4 records. So what would be the generated output of this SQL statement? So we have select ID, name, age, amount from customers orders, where customers.id is equal to orders.customer ID. So we have customer ID 3 which is Kaushik. So customer ID came from the table 2, and the um, the name came from table 1. Okay, so we have 3 Kaushik. Okay, and then we have another 3 Kaushik here. We have the same customer ID here from the orders table. And then we have 2 Kilan. So 2 here, customer ID 2 here represents Kilan, which is the same ID for from table 1. And then for Chaitali. So this will be the output of our statement here. So the SQL union clause operator is used to combine the results of 2 or more select statements without returning any duplicate rows. To use this union clause, each select statement must have number 1, the same number of columns selected. Number 2, the same number of column expressions. Number 3, the same data type. And number 4, have them in the same order. So the basic syntax of a union clause is as follows. We have select column 1 to column 2 from table 1, table 2, where condition union select column 1, column 2 from table 1, table 2, where condition. So let us join these two tables in our select statement as follows. Select ID, name, amount, date from customers. Left join orders on customers.id is equal to customers orders.customer underscore ID. Union, select ID, name, amount, date from customers, write join orders on customers.id is equal to orders.customer underscore ID. So again, we will be using the same table. So table 1, known as customers table, which consists of ID, name, age, address, and salary as its fields. And it consists again of 7 records. For table number 2, which is known as orders table, consists of OID, date, customer's ID, and amount, and consists of 4 records. So if we're going to apply this statement, if we're going to join these two tables using our select statement, so we will come up with the following output. So we have 4 columns for our output, which consist of ID, name, amount, and date. So we have 1 Ramesh. The amount is null and the date is null because there are no records for ID number 1. Next, we have number 2, which is Kilan. The amount is 1560 coming from the orders table, and the date is 2009-11-20. For ID number 3 from table 1, we have Kaushik, which is the amount is 3,000 and the date is 2009-10-08. So there's another customer ID, which is also number 3. So we will just copy the name Kaushik and the amount is 1,500. So the date is 2009-10-08. Next, number 4, ID number 4, Chaitali. The amount is 2,060 coming from the orders table, and the date is 2008-05-20. 5, Hardik. The value of the amount and date is null because there is no matching values here for table 2, which also applies to ID number 6, Komal. So null values again for amount and date. So no matching values for table 2. And ID number 7, Mafi. So null value for amount and date because there is no matching value again from table number 2. So that is how we apply this select statement